All right, everyone, Mr. Graham here. Today I want to start talking about the concept of free fall. And I do want to stress that in physics, you really want to make sure you understand what's going on before when you move on to the next topic, whenever you're learning physics, because we tend to build on things. And to illustrate that point, we're going to study a different type of motion today. It's going to be free fall. However, as you'll see when we make our motion graphs for an object in free fall, we will be still dealing with uniformly accelerated motion, or UAM. So you really got to understand the kinematics of one-dimensional motion in the x direction or the horizontal direction. And if you do, then all you need to do is extend those concepts to the vertical direction. And the problems are exactly the same. You'll see that the graphs are very similar. And so just keep that in mind. If you understood kinematics so far, then this shouldn't be too difficult for you. Let me move me out of the way. So I have an object here. This vector here represents an acceleration, and the acceleration due to gravity gets the symbol g, little g, lowercase g. I have a position or a distance versus time graph on the left. I have a velocity versus time graph on the right. And but notice this is in the y direction. So my position in the y direction. So the only thing that we're really changing now is instead of dealing with horizontal motion, we are dealing with vertical motion. And so you might remember when we were dealing with horizontal motion, we were talking about motion in the x direction. Now we're talking about motion in the y direction. So this graph here would actually represent kind of like our normal XY axes like we're used to seeing in our math class. Remember when we talk about just the x direction motion, we plot that distance traveled in the x direction on the vertical axis on our motion graphs, on our distance time graphs or position time graphs. But now we're going to be dealing with the y direction motion. And since we're dealing with the y direction motion, we will then be plotting the y direction motion on the vertical axis and still time on the horizontal axis. Okay, so real quick, what is free fall? Free fall is just an object that is moving through the air under the influence of gravity only. So some people, and the colloquial or everyday usage of the word free fall is if you just drop an object and it falls straight down. But from a physics perspective, free fall happens to an object could be moving up and it's in free fall. It could be moving through an arc through the air and it's in free fall. If it's moving through space only under the influence of gravity only and no other forces, then we say the object is in free fall. If you notice down here on the right, let me get rid of this. If you notice in the bottom right here, this little icon, if I turn that off, I'll actually turn off air resistance. And so at first here, I'm going to turn off air resistance. And for pretty much all the problems that we deal with where you have to calculate, we neglect air resistance. As you'll see, when you have air resistance, the acceleration of the object is not uniform. And so we aren't dealing with uniformly accelerated motion. And so our kinematic equations actually won't work, and we need a higher level mathematics, which we're not even going to cover in on level or pre-AP or even AP Physics 1. We just don't deal with that. But you want to kind of understand what air resistance does to the overall acceleration of the object, which we will talk about today. So again, free fall is just the motion of any object that's only being influenced by gravity. And for the most part, we're going to neglect air resistance. You can pretend that we're just in a room or in a space where there's air so we can breathe and we can still survive, but that the air resistance won't play a factor. And air resistance does, in fact, if you're ever driving in your car and you stick your hand out the window, you're going to feel that air resistance pushing your hand back. If you ever go skydiving, whenever you're falling down, you definitely feel air resistance. But in our introductory study of physics, we don't really deal too much with air resistance. Okay. So let's look at the velocity graph here. Let's look at the velocity graph. When I hit play, the object is going to start falling. And I get my position versus time graph. Since we are accelerating uniformly, then we do have a parabola for our position time graph. It's only half a parabola at this point because we just started with downward motion. And then my velocity graph is going to be a straight line with a negative slope. If it has a negative slope, it has a negative acceleration. Remember, velocity versus time graphs, you have negative acceleration. And let's look at the values here. Let's look at after 1 second, the object is moving at approximately 10 meters per second, negative 10 meters per second because it is traveling downward. After 2 seconds, we're pretty close to negative 20 meters per second. At 3 seconds, we're pretty close to negative 30 meters per second. And at 4 seconds, we're pretty close to negative 40 meters per second. So very often, and even on AP exams for this stuff, very often we approximate the acceleration due to gravity as being, and remember, the acceleration due to gravity, we get a special symbol G, and that is going to be if we're approximating it, we can approximate it pretty close to 10 meters per second squared. It's not exactly 10 meters per second squared because well, the Earth if the Earth just had a little more mass, or if it was a little smaller in radius, then it would be pretty close. It would be closer to 10, but this is approximate. So I probably should have not drawn an equal sign. I probably should have just drawn the little approximately equal to. Accurate to 3 significant figures, the acceleration due to gravity is actually about 9.81 meters per second squared. And we usually, even if we're doing the more accurate value, we just round that to 9.8 meters per second squared. For most cases, that's a good enough approximation. So what this means is that the object's speed increases by about 10 meters per second every second. And so that's why up on our velocity time graphs, after about 10 seconds, after 1 second, we're traveling at about 10 meters per second. At 2 seconds, we're traveling at about 20 meters per second speed. I'm talking speed here, so I'm not talking the directions. When we are dealing with our coordinate axes, where up is the positive direction, then we would say that the acceleration is actually negative because it does point down. We can see the vector right here, that G vector does point down. And so keep that in mind as well. Okay, so let's dig into, let me clear my screen here and let's dig into this a little more. All right, so let's start this motion again. And let's go ahead and hit play. All right, so notice that my velocity is obviously increasing during this time. My acceleration is staying the same. As long as you're not traveling miles and miles and miles in the vertical direction, the acceleration due to gravity is constant at the Earth's surface. It is that 9.8 meter per second squared acceleration, or approximately 10 meter per second squared. Note that because it's not exactly 10, after 1 second, you're actually, if you were to go skydiving and there's no air resistance, after 1 second, you wouldn't be traveling with 10 meter per second speed. You'd be traveling with 9.8 meter per second speed. The next second, you'd be traveling with 19.6 meter per second speed. And after another second, you just add 9.8 meters per second every second. And that's how fast you're getting fast when you're in free fall with no air resistance. But again, most of the time we kind of approximate it. After 1 second, we're going 10 meters per, if you're just like saying approximately, well, after 5 seconds, we're going approximately 50 meters per second, and so on. Okay, so keep that in mind. After 5 seconds, you'd be going approximately 10 meters per second downward, or with your speed would be 10 meters per second. Sorry, I said 5 seconds, right? After 5 seconds, your speed would be approximately 50 meters per second. Your velocity, though, would be negative 50 meters per second because your velocity does point down. In reality, after 5 seconds, I just multiplied that out because I can't do on my calculator, because I can't do that math in my head. You'd be going not 50 meters per second speed, but actually 49 meters per second speed. So it's pretty close to 50. And we can see that on the graph here. If I let it go to 5 seconds and I go to 5 seconds at when x equals 5 seconds right there, my y value, which in this case tells you velocity, which you can see in that little box, it's negative 49 meters per second. It's pretty close to 50, but not quite. So again, when we're approximating it, we'd be going 50, but in reality, we'd be going about 49. Okay. Now let's talk about what would happen if we actually had air resistance. So I'm going to let this go for a little longer just so I can get a graph that's a little bigger. And then I'm going to do this experiment again. I'm going to leave those graphs up, and then I'm going to turn on the air resistance. And then watch what happens. Let me get rid of the vector here so we're not focusing on that. Let's just look at the graphs here and look what happens on the acceleration graph, or the velocity versus time graph. Remember, the slope there tells us the acceleration. And now we do have air resistance. And now we see that the acceleration is definitely smaller, and it does change. And again, if we're changing acceleration, we are not undergoing uniformly accelerated motion. So our acceleration gets reduced, but the kinematic equations won't work. And that's why we don't really deal with air resistance in introductory physics classes. If you want to learn how to treat air resistance, then take AP Physics C next year. And that's something that we definitely do in that class. Okay. So if you ever go skydiving, what I would suggest is watching a video. There's a few years ago, there's a guy that took a weather balloon or a balloon up like almost out into space. He actually had to put a spacesuit on, and he went skydiving from there, and he jumped out pretty much out, I wouldn't say out of the Earth's atmosphere, but so high up in the air that the air is so thin that there was very little air resistance. And he picked up speed up to like 700 or 800 miles an hour. He was traveling before he actually started getting slowed down by the air. If you ever go skydiving, you never go faster than about 120 miles per hour. And that's because you actually have air resistance that fights the force of gravity. And so with the air resistance on, I'm going to turn on my velocity vector. And I'm going to have the values actually shown, and we can see what happens when we reach what's called terminal velocity. So the object will fall, and it'll keep falling. Notice that its acceleration is decreasing because the slope over here is decreasing, and eventually the object will be falling at a pretty constant rate. So in this case, we'll reach terminal velocity at about 31 meters per second, a little more than that. So right here, we got 31.04 meters per second. Notice that our parabola that we expect on a distance time graph for accelerated motion then becomes linear. Once it's linear, you're traveling at constant speed. We should know that at this point. Also, our acceleration on our velocity time graph, remember the slope here represents acceleration, but because of air resistance, when we reach terminal velocity, the acceleration is 0. And so that means our slope on our velocity time graph is 0. And that's why I'm saying if you ever go skydiving, you end up reaching a terminal velocity of about 120 miles per hour. And all that means is that the downward force of gravity is being completely offset by the upward force of air resistance. And so that at that point, you then have terminal velocity, and you're not going to be picking up any more speed. Now you can change that when you're skydiving by just changing the way that you orient your body when you're falling, because air resistance is pretty complicated. It's a function of several variables, including like the shape of the object and the orientation of the object. But again, we don't deal with that in introductory physics. Just one take-home point here: if we are dealing with if we're not dealing with air resistance, which is going to be the vast majority of the time, then let me erase the graphs. Then the acceleration, then the velocity versus time graph and the position versus time graphs are exactly what we expect for just uniformly accelerated motion. We have a nice parabola in the y direction and a velocity and a linear graph for the velocity versus time graph. Now I want to end by showing you what it would look like if I instead gave this object an initial velocity in the y direction. Let's say we give it 5 meters per second in the y direction. I'm going to slow down time a little bit so we can kind of watch what happens. And we get something similar, but there I get the other side of the parabola. Remember, slope on a distance or position versus time graph tells you velocity. So I start with a positive velocity, but it slows down. The velocity slows down. And then at the top here, that's when we reach 0 velocity. And then we start picking up speed in the negative direction, right? And if we look at the velocity versus time graph for this interval, this was an answer on a worksheet on kinematic equation worksheet number 1. At the last problem where it asks you to sketch the graphs, this is what it looks like. I start with an initial velocity, and then so on my velocity time graph, I started with 5 meters per second velocity, and I decrease. I'm decreasing, I'm slowing down, and then eventually I hit 0 meters per second. That's when I'm at the top of my motion, and then I start picking up speed in the negative direction. Okay. All right. Well, that's your introduction to free fall. We're gonna learn a little more about this in the coming days and start solving some problems. Again, if you know how to deal with kinematics in the horizontal direction, kinematics in the vertical direction is no different. All right. See you in the next.